Hello, this deals with section 3.2, which is graphing polynomial functions. And we're going to start by first talking about what a polynomial is or what a polynomial looks like. So I'm just going to write a basic thing and just going to walk you through some of the terms that they have listed on here, just to kind of give you an idea if you ever hear your instructor or myself later on in one of the other things talk about what these things are, you'll have an idea of where to locate them at. First thing that we're going to look at is we're going to look at that number there. That number there is known as the degree. Now, the degree is nothing more than the highest exponent. Okay, that is what the degree is. So if someone asks you for what the degree of the polynomial is, it's referring to what's the highest exponent. Okay, so that's what they're referring to. Then the second thing that we're going to focus on are these numbers right here: the 3, the 6, the -2, and the 1. All of those are what we call coefficients. Now, coefficients are nothing more than the numbers in front of the letters. Okay, if you notice, they're in front of all the letters X, but that's all they are, is just the numbers that are in front of the letters. This one here, if there isn't a 1 there, it's understood to be a 1, just so that you have that idea that there's always a number there, even if there's a letter, there's always a number there. This number right here is important. That's also known as the constant. Now, I referred to this in section 3.1 as the y-intercept, which is correct. If you put 0 in for x, you're going to get that number no matter what. So whatever the number that does not have a letter is known as the constant, but it's also the y-intercept. And the last thing that I have that's in there is this thing right here. That whole group right there is known as the lead term. Now, why is it known as the lead term? Because it is, in fact, in front of, or has the one that has the highest exponent. It has nothing to do with the order that it's in right now. It has everything to do with the fact that it's got the highest exponent involved in that term. It is the degreed term, or whatever you want to call it. Then this number specifically is known as the lead coefficient. So we will use that here coming up when we talk about things like end behavior and whatnot like that. But that is what, if you ever hear me refer to those terms, that's what I'm referring to when it comes to a polynomial. Okay. Now, first thing that we're going to do is we're going to just graph these things. And before I graph them, I'm going to talk to you about end behavior. Now, what happens most of the time is you get this nice viewing rectangle on your graphing calculator, and it might look like this, and you get this parabola looking shape that comes in here, and you think, oh wow, that's such a good window. But realistically, what you don't see is you don't see that it really turned around back here and went that way, and it turned around out here and went that way, and you don't get any of that information from the graph at all. That's a problem. Okay, so what we look for is we look at a couple different things that will tell us whether or not and how it's going to finish and how it's going to open and everything like that. This window would not be good enough. You would need to move to the left, which affects the x minimum. You would want to move to the right, which affects the x maximum. And you'd want to definitely move up, which would affect the y max. Now the down, if you needed to go down, would be the y min, and those are all found in the window. Like when you go to, like I'm referring to a Texas Instruments, either 83 or 84. Those would be specifically in the window button. That is, if I remember off the top of my head, either the second or third one across the graphing buttons along the top. It'll say the word window. You push that, and those are the things that you would adjust. Setting an appropriate window is kind of like a crapshoot. It might not be the window that I chose, but it might be a window that would be just as good as mine. So just so that you are aware of it, there are multiple options for windows that would work for all of them. So it's basically a guess and check. Guess at a number and see if it works. If it doesn't work, try again. If it does, you found one. So Not a big deal. But for this particular thing, we do have some things that help us figure out what happens and how I knew that that was not a good window. End behavior is what's happening on the ends. Now, if it has an odd degree, it will do something different than if it has an even degree. Now, when we mean by even and odd, we're not referring to the function being even or odd. We're referring to the exponent, that highest degree exponent. Is it an even number or an odd number? That is all that we're referring to. Now, the other criteria is if the lead coefficient is positive, or if the lead coefficient is negative. Okay, and actually I'm going to scoot over this odd degree thing just a little bit, just so I can kind of make it in like a chart type format. Odd degree. Okay, I hope this makes sense, and I'll try to walk you through it here a little bit. If it has an odd degree and the lead coefficient is positive, then here's what it's going to say. It's going to say y approaches negative infinity as x approaches negative infinity, and y approaches positive infinity as x approaches positive infinity. Now, just to kind of give you a little side note, an asterisk or whatever you want to call it, when it says y is approaching negative infinity, that's the same as down. And when they say y approaches positive infinity, that's the same as up. And when they say x approaches negative infinity, they're saying left. And x approaches positive infinity, they're saying to the right. Okay, that's in layman's terms what that means. But when I refer to those technical terms, that's what they're saying. So this first one says y approaches negative infinity as x approaches negative infinity. They're saying as you go to the left, it's going down. And then the second part of that, as y approaches positive infinity as x approaches positive infinity, as you go to the right, it's going up. That's what it's referring to. Now, on the other hand, if it's a negative, now it's going to do exact opposite directions. As y approaches infinity, as x goes to negative infinity, or left. Y goes to negative infinity as x goes to positive infinity, or as it goes to the right. Basically what this one is saying is that it kind of flows uphill, and this one flows downhill, is what that's saying for that first one. Now when we deal with an even degree, I'll switch colors here for this one. When we're going with an even degree and a lead coefficient of positive, y is going to approach positive infinity as x approaches positive infinity. Oops, we'll go negative first, sorry. Negative infinity. And then y also approaches infinity as x approaches infinity. So here's what this is saying. As you go left, it's going up, and as you go right, it's going up. It's going up on both ends is basically the gist of it. And then the next one is y approaches negative infinity as x goes to negative infinity, and y goes to negative infinity as x goes to positive infinity. So a lot of it again is this one's going both down. Okay, so if it's an even degree and it's a negative, they're both going to go down. If it's even degree and positive, it's both going to go up. So up would be like a parabola going up. Something like that would be both down. Very similar to that one I showed you at the beginning before I gave you this little chart. So why is this important? I'm going to go back one slide. This would have been something that would have had an x to the fourth, and it would have had a negative in the front of it. Now x to the fourth, 4 being the even, and that being odd, and that being negative, I know that it's going to go both down, and this window does not show both down, it shows both up. So that means, hey, you need to make your window bigger, or figure out what's happening with your window. So that's what I mean by this, is that we'll know based off of just looking at the exponents and looking at that lead coefficient. So if I had something that had a polynomial that had 3x to the fifth, blah, 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 I would know based on this, if that was my degree, that I should finish with an odd degree, and that is an even, and that's a positive number, so that should flow uphill. That's how it should flow. So on the left it should go down, and on the right it should go up. Now another thing that could happen in here is that with a 5 being the highest exponent, we could have potentially 5 different times that it crosses the x-axis. I say potentially because that's real. Reals, it doesn't necessarily mean it's all reals. So if it's not, then we might only have 1 or 3. But we could have up to 5. But it also could mean if you take that number and decrease it by 1, that could be how many turns you have in that. So if I really wanted to make something that looked like this, 1 turn, 2 turns, 3 turns, 4 turns, that would be more better representation of a potential what we could see with that. Just based on me finishing high, or finishing down there, or starting down low and finishing high, and having 1, 2, 3, 4 turns based on 1 less than the highest exponent. And also it could potentially hit the x-axis 5 times. Does it have to? No, but it could, is what we're saying. So in the next part, we're going to find zeros in order to help us graph a little bit. Now, realistically, I'm pretty sure that most people would use their graphing calculator in order to graph things, which, you know, me as an instructor, I am just fine with people using their graphing calculators to their advantage. The only thing that I, caution you on is that pay special attention to when it gives you the x's and y's, that you're not saying, 2.34 when it's 2.34 times 10 to the negative 20th or something like that, which that's basically 0. So just be careful. But if it asks you to find the zeros, one of the things that we usually do is we try to factor it if we can. If we can't factor it, we can't factor it. But if we can factor it, it's easier. The more dots you put on a graph, the better looking graph you're going to make. Now, just about anybody can put the polynomial into your graphing calculator, but can you produce it on a piece of paper? That's the issue. For me, if I can factor this, I'm going to. So the first thing I always look at is there anything I can take out of all 3 terms? And there is. I can take an x out. When I do that, I end up with x squared minus 2x minus 3, and now that's a quadratic, which when I factor that, again, it gives me x and x, it gives me minus 3 and plus 1. Now from there, if I set each group equal to 0, I got x equals 0, x equals 3, and x equals negative 1. Now why did I do that? That is for me to put on my graph. It's going to make my graph better. Now, with end behavior, that's a 3, which means it's odd, and that's positive, which means I know it's supposed to go down this way and finish up this way. I also know with a 3 that I should have 2 curves. Now, not knowing anything in between here, I'm just kind of rough estimating that it's probably a little bump there and a little bit bigger bump there. Now, without having to put this into a graphing calculator, I've just assumed. If you don't want to use a graphing calculator, what I would suggest that you do is insert random numbers for x, like 1 and 2, see where those ordered pairs are, and sketch them, and then connect the dots. If you use a graphing calculator, you should see something similar to this particular shape. Okay, and most people use a graphing calculator. They find it easier, whether it's a Casio or a TI. I usually use a TI, but I know some people prefer Casios out there too. But another one, just to kind of give you an idea that it will still work, is if I factor by grouping. Now when I have 4 terms, I usually group those, which means that I put the first 2 together and the last 2 together. And what I'm doing is I'm taking out the common thread between the front group and the back group, and what I'm hoping to see is that this and this are exactly the same, which they are. Then when I put whatever is left inside, or if I factor out that x minus 2 group, I end up with x minus 2 times x plus 2 times x minus 2 again. Notice how I have this one and this one in there twice. Some people write that like this, where they would go x plus 2 and then x minus 2, the quantity squared. They're both correct. It does not matter how you draw it. Now when you see one that shows up more than once, that's known as a multiplicity of 2 in this case, because it showed up twice. If it shows up 3 times, it's known as a multiplicity of 3. 4 times, multiplicity of 4, and so on. Whenever you have an even multiplicity, what usually happens is I kind of imagine a bouncing ball. If I were to throw a ball up in the air and hit it, and it was a bouncing ball, it would bounce and then go back up. Very similar to if it's got a multiplicity of 2, is that it will bounce and come and go right back to where it came from, or not right back from where it came from. It will go back up or go back down depending on if it came from the bottom or top. And what I mean by that is when I go to graph this, negative 2 is this one, positive 2 is this one, with an exponent of 3, I know that it probably, and a y-intercept of 8. 4, 5, 6, 7, 8. I know that it probably did something like this. It came in through here, because that's one of the zeros, and I know that that's odd with a positive. It hit here and came down, and then touched it, and then went right back up. And because, like a bouncing ball would hit the ground and come right back up, because it had a multiplicity of 2. If it has an odd multiplicity, it actually strikes through it. It goes right through it and doesn't stop. Now, another thing that you could also do is you could also find these points specifically, and those are the turning points, are also known as the extrema. Okay, the local extrema, minimum and maximum. We did this already before in chapter 2 when we dealt with finding the intervals in which it's increasing and decreasing. We found those. So that's not a new concept for us. But local extrema are basically just the highest degree minus 1, and then that's how many turns they could have. Okay, it doesn't necessarily mean that, but that's how many you could have. Now, me personally, what I would do is I would try to label and list everything you could on it. I would be labeling my x-intercepts, labeling my y-intercepts, finding the extrema. Okay? So that way, if you have all those ordered pairs on your graph, it's going to make your graph look better. Okay? And a lot of that you can get right off the calculator, but some of it might not be so bad just to factor it. So with that, that's really about it for section 2. Thank you.